Hello, welcome to episode 4 of Multivariable Physics. Today we're going to be talking about derivative rules for multivariable functions. And this is going to be a very quick episode because they are the same. That's basically like, if we have nabla f plus g is just equal to nabla f plus nabla g. We have nabla k f, right? K is some constant, right? K is just real number here. We only care about real numbers right now. Then this is just k nabla f, right? And then if we have nabla f times g, or f over g, well, then we just apply, the quotient rule, g squared fg, right, minus gf. And then here we actually don't use the derivative. We would use, so this would be prime f, or nabla fg plus g nabla f, right? And so kind of an interesting word here that I want to mention is that I didn't quite touch on this in the last episode, but remember how we think of nabla as being some vector, right? Well, this is a vector space of sort of functions. That's kind of when I think about it. The field, you know how we take vectors and we can scale them by some a, right? This nabla is some vector. You can think about it as like, built of unit vectors of, y hat, x hat, right? You can think of this as like being composed of these unit vectors in which are tiny derivatives, right? Or infinitesimal changes in space, right? If you think about these being the basis for the vector space of nabla, what we can kind of think about is, well, we can think about what happens if we scale nabla, right? So we scale it by some constant. This becomes f prime y. It's much larger, right? And then change in x f, right? We scale nabla by functions, okay? Or functions form the field, right? Of our vector space. So, and I'm sorry, I have terrible handwriting, but and so that's kind of where this intuition kind of makes sense, where we can, okay, well, g times nabla f, what does that mean? If these are both functions, well, you're taking nabla and you're applying it to f. This is a vector, and then this g is a scalar. So all we're doing is scalar times vector multiplication, which is a vector, which is a derivative, which this vector is going to be some gradient, and this same stuff applies here, right? And same stuff applies here, which is dividing by this scalar squared. That's all that is. It has this exact same intuition as if these were numbers, and it was like some vector v. You can kind of think of this as some vector v a over b is equal to vector a times b and minus vector b times a over b squared. Same intuition. It's just it's just a kind of different way to think about the arithmetic on over vectors here. But the way you would apply nabla and then apply nabla f and then apply g is the same as if you would just scale a vector and then multiply that scaled vector by some other number. And so you could try some examples out. A nice one, just x squared y is going to be f, okay? And then let's suppose g is equal to y 2yx. Okay. Well, what is x squared y 2yx? Right, if you multiply these, what is nabla? Well, and this is going to be nabla f, so that's 2x, or 2xy, x squared times 2yx minus is going to be 2y 2x times x squared y over 2yx squared. Okay. And yeah, so you can go fill that out. You could also just directly compute at 2x cubed y squared, the nabla of that, which is going to be 6x squared y squared 4x cubed y. And then if you run and check, these are going to be the same. And I hope that answers that. One thing I haven't talked about is the chain rule, and I'm going to get into that quickly. That's the one thing that is a little different. There's a few different ways to talk about the chain rule, especially multiple dimensions. So I'm going to be kind of brief here. Oops. Sorry for that. So the first thing to kind of consider when we take these derivatives is actually that we are doing, sorry, I dropped my notes, but yeah, so there's actually I'm just gonna make that its an own episode, the chain rule, because there's a few different ways to take it, a few different moving parts, and it's gonna make more sense if I deal with it alone. But yeah, just remember that nabla is pretty much just like a vector, and these functions are like the scalars that you're scaling this vector. And as you apply, you can just kind of apply nabla to each one, and it has the same derivative rules as you have in regular calculus. All right, so yeah.